Let's look at a topic that's commonly referred to as curve sketching. It's where we're making the connections between the function, the first derivative, and the second derivative. So we have some details here about the first derivative. So if the first derivative is 0 or the first derivative is undefined, then f of x has what we call a critical point. Many times this critical point can turn into a max or min on the graph of the function, but it's just a point of concern that we want to use, and we'll show you how to test for those other values. Now, if the derivative is greater than 0, meaning it's positive, then the function is increasing. And vice versa, if the derivative is less than 0 or the derivative is negative, then we know the function is decreasing because the slopes of the tangent lines are negative, and that shows us then that it is decreasing. If the first derivative changes from a positive, the slopes are positive, to a negative, then the function has a maximum. And if the derivative changes from negative to positive, then the function has a minimum. So let's take a look at a function, and you might want to make a note. This first one is going to be primarily what you would do without your calculator. So we want to determine where a function is increasing, decreasing, has a max and min, and of course we want to show our analysis for that. So everything begins with the first derivative. So we'll do the power rule. To get our first derivative is 4x cubed minus 12x squared. Now, as we stated, when the derivative is equal to 0, we have a critical point. So we begin by then setting this equal to 0, and we solve, looking for that GCF being 4x squared. And so we can see that x would be 0 from here, or x would be 3 from the parentheses. These are called our critical points. And what we do with those critical points is we put them on a number line. You know me and my handy dandy Sonic gift card here. Now be sure when you use a number line for your analysis that you label that number line. AP likes you to make sure you label what it is you're going to be testing. So I'm going to put my critical points on the number line, and I'm going to test each of these intervals. Now let me do it with one that's pretty easy. Like I'm going to test x equals 1 because it's between 0 and 3. I'm putting it into the factored form of my first derivative. Follow my line of thought here. If x is 1, this is positive. And 1 minus 3 is negative. So a positive times a negative would make this interval negative. The derivative is going to be negative in this interval. Let's test this interval. We'll test negative 1. If x is negative 1, then this again is positive. And this is negative, right? Negative 1 minus 3 is negative. So you have a positive times a negative. Now, friends, I'm not really concerned about the value of the derivative. I'm more concerned, is it positive or negative? Next, let's test x equals 4. Again, I get a positive, and now 4 minus 3 is also positive, so I get a positive here. Now, let's answer the question then, now that I've done my analysis. Where is the function increasing? The function is increasing where the derivative is positive. I know the derivative is positive on this interval. So on the interval from 3 to positive infinity. I didn't include the 3 with a bracket because remember the derivative at 3 is 0. So it's not positive at 3. The function is decreasing on the intervals where it's negative, where the derivative is negative. So that's from negative infinity to 0, and then from 0 to 3. And again, I have to break it up at 0 because the derivative at 0 is 0. So now my derivative, let's see, derivative changes from a negative to a positive. That's a minimum. So f of x has a minimum at x equals 3. And the number line justifies all my work here as long as I've labeled it. So good details there from our number line. And so the top here goes into a little bit of detail about those critical values. Let's take a look at finding the intervals where this function is increasing and decreasing or has a relative max or min. So let's start with that derivative again. The derivative of f of x, we're going to bring the 2/3 in front. 2/3 x plus 2 to the negative 1/3. And then, of course, the derivative of 0. I'm sorry, a derivative of 1 is 0. Let's clean this up just a bit by moving that to the denominator. Okay, now when I try to set the derivative equal to 0, I want you to see what happens. I cross multiply here and I end up with 0 equals 2. Now we know that's not true, okay? But I need to look at my derivative again because it's got a denominator. So what value is going to make that denominator equal to 0? And the reason I'm checking this is because this is where the derivative doesn't exist. It's also a critical point. So we have a critical point at negative 2. That means we potentially could have a max or a min there. We need to test it with our number line. We'll put negative 2 on there. And let's test, we'll test the easy side, right? We'll test x equals 0 first. Put it in our derivative, okay? 0 plus 2, still positive. Cube root of 2 is positive. 3 times cube root of 2 is positive. Still, everything's pretty positive there. Notice I didn't look for the values, okay? Now over here, let's try negative 3. So I've got negative 3 plus 2, that's negative. Cube root of negative is negative. 3 times a negative is negative. 2 divided by negative is negative. I'm really just concerned about those positive and negatives. Okay, so the function I know now is increasing on the interval from negative 2 to positive infinity. And the function is decreasing on the interval from negative infinity to negative 2. And I know, because it changes, the derivative changes from a negative to a positive, I know there's a minimum at x equals negative 2. Now, let's use the graphing calculator to take a look at why this is all happening. So let's go to my y equals. Let's put in our equation, x plus 2 to the 2/3. Be sure and use your arrow to come out of the power there, and then plus 1. I'm going to draw a rough sketch of our graph here. I'm not going to plot exactly, although you could if you want. Okay, we have a minimum there. We call this a cusp, is what this feature of the graph is called. Okay, and we learned previously that this is a place where the derivative doesn't exist. However, the function does, and you can have a minimum there, or you could have a maximum if we're happen to be turned upside down. So good place things to look at for critical values being where the derivative equals 0 or where the derivative does not exist. So I'm going to switch back to our form. We've got a couple of things here. of note that I think are very important. We're told that the first derivative identifies where the function is increasing, decreasing, and where it has a max and min. In a similar way, the second derivative tells us where the function is concave up or concave down and where it has a point of inflection. Those may be new words for you. That's okay. We're going to explain them. But I also want you to see this last statement, which is very important. Since the second derivative is the first derivative of the derivative, all the same relationships between the function and the first derivative apply to the second derivative and the first derivative. I know that gets a lot wordy, but I thought this was very, very important to point out for us. So let's make some connections about the second derivative. If the second derivative is equal to 0 or is undefined, then the first derivative has critical points. The function could have, and I'm saying could have for a reason, points of inflection. And the reason I say could, because we have to make sure that it changes, the second derivative changes from a positive or a negative in order for the function to have a point of inflection there. Okay, if the second derivative is positive, then the function is concave up. And for your notes' sake, I want you to have like a sketch of what concave up looks like. I like to think of it like a parabola turning up. So the shape could be something like that or something like this. It's that parabola shape turning up. And if the second derivative is positive, then the first derivative is increasing. Now, if the second derivative is negative, vice versa, we'll have the function is concave down, and the first derivative is decreasing. And let me draw a connection of what concave down means. It looks like a parabola turning down for that portion of the graph. Now, if the second derivative changes from a positive to a negative, then of course the function has a point of inflection. And if it changes from a positive to negative, the first derivative has a maximum. And then, of course, we have the same thing when it changes from a negative to a positive on the function. But we have a minimum on the graph of the first derivative. Okay, now very careful. This is going to be a chart that you're going to go backwards and forwards in, okay? It's going to be something I want definitely in your notes because you want to have all of those relationships. You're going to be asked to know them, okay? So previously we found the first derivative. Now we're asked to find the second derivative of it. So I'm going to rewrite that first derivative. I'm going to rewrite it back as 2/3 x plus 2 to the negative 1/3. And I'm going to take the second derivative. So I'm going to bring that negative 1/3 in front. That'll give me negative 2/9 x plus 2 to the negative 4/3. Okay, so just like before, we can rewrite this and set it equal to 0. Okay, just like before, we're still not going to get any values where the second derivative equals 0. That just doesn't happen. So we have to look at where it's undefined again. And it's undefined again at x equals negative 2. So let's put that in words. F double prime is undefined at x equals negative 2. Okay. Now we're going to do another number line, but this time we do it with the second derivative. Do another number line, but this time do it with the second derivative. We're still going to put -2 on it because that's where the second derivative is undefined. We're still going to test each side of the -2, but we're going to test it in the second derivative this time. So let's do the easy one. We'll test x equals 0. So you can do it from either form, but we're putting in 0 for x. Positive, positive, multiply by 9, positive, but we're dividing by 2, dividing with -2, so that's going to give me a negative on top. Okay, then we'll test the other side. Let's test x equals -3. Okay, so -3 plus 2 is -1, right? Cube root, but then I'm going to the fourth power. Anything to the fourth power is going to be positive. So I get a positive times a positive, and then I'm dividing with a negative, so I'm getting a negative again. So what does that tell me? Well, that tells me that the function is concave down on the interval from -infinity to -2 and from -2 to positive infinity. It's concave down everywhere except at -2. And because we didn't change concavity, we didn't change from a positive to a negative or a negative to a positive, we don't get a point of inflection here. Think about what that graph looked like. I'm going to bring our graph back up. Looks like a parabola turning down, right? And it doesn't change when you get to -2. It just changed from decreasing to increasing, but concavity did not change. Okay, lots of good connections here between the derivative, the first derivative, the second derivative. Let's see if we can complete these statements based on what we've kind of discussed so far. Okay, so if the function's increasing, then the first derivative is positive. Vice versa, if the function is decreasing, the first derivative is negative. If the function, we're on number 3, has a relative max or min, the derivative changes from negative to positive. That's for the max. Or it changes from positive to negative. Okay? If the function has a point of inflection, the first derivative has a max or min. Okay, if the function's concave up, the second derivative is positive. Vice versa, if the function's concave down, the second derivative is negative. Test yourself with these. You can pause the video and try and see if you can complete these. Okay, if the function has a point of inflection, the second derivative changes from positive to negative, or changes from negative to positive. Okay? If f prime is increasing, so if the first derivative is increasing, the second derivative is positive. If the first derivative is decreasing, the second derivative is negative. If the first derivative has a max or a min, then the second derivative changes from positive to negative, or changes from negative to positive. Okay, if the first derivative has a point of inflection, the second derivative has a max or min. Okay, now if the first derivative changes from negative to positive, the function has a minimum. And vice versa, it has a maximum. If the first derivative has a max or a min, the function has a point of inflection. And if the second derivative changes from a positive to negative, then the first derivative has a max, and vice versa, the first derivative will have a minimum. Okay, this is a great list to practice with. Quiz yourself back and forth on these to make sure you know which one tells you, because you're not going to know. Are you going to be looking at the function, or are you going to be looking at the first derivative? You won't know what the question will be until you're told. And so quiz yourself on these. These connections are uber important. Now, on the following pages, I'm not going to take time in my video here. You have a great activity, a very classic activity where you are trying to match a derivative, a function, a derivative, and a second derivative together. This is a great activity if you want to cut these cards apart and match them to each other. Practice, practice, practice makes progress. So check out those to help with matching the function to the derivative to the second derivative. So let's take a look at this function. Actually, it's the derivative we're looking at. So we want to tell information about concavity, so concave up and concave down, as well as point of inflection, but we're starting with the derivative. So let's take the derivative of the derivative, which would be our second derivative. And it looks like it's going to be a quotient rule. So I've got the bottom times the derivative of the top, which is negative 12, minus the top, which is negative 12x, times the derivative of the bottom, which would be 4x cubed plus 12x, all over the bottom squared. Okay, a little bit of cleanup here. I'm going to distribute the negative 12. And then I'll distribute the 12x here. And then I'm going to leave this denominator pretty much alone. And the reason I'm going to do that is because, one, it's not going to really matter when I set the derivative equal to second derivative equal to 0. And also because it's being squared, I know it's going to stay positive. So when I get ready to test intervals, it's not even going to be a problem. Okay, let me pick up some like terms here. I've got 48x cubed. Then I've got 72x squared and 108. Okay, so now we're going to set the second derivative equal to 0. Now, this is where I talked about how the denominator did not matter. Okay, so instead of carrying it around, I'm just going to drop it, because when we multiply both sides by that denominator, it's going to become 0. Okay, let's see. Looks like these are all divisible by 12. Yes. So let's take out a negative 12. Leaves me with x to the fourth minus 4x cubed minus 6x squared plus 9. I was thinking about factoring by by grouping, but that wouldn't work here. So I'm going to see, looks like 1's going to work. I'm going to check out my calculator. Let me pull my calculator up for us to take a look at. And I'm going to put this into y1. I'm not going to put the negative 12. Let's just do the x to the fourth, because that's what I'm trying to solve for. So I got x to the fourth minus 4x cubed. And then come down out of the exponent, plus, minus 6x squared, and then plus 9. And let's take a look at what that looks like. I know x equals 1 would work, but I need to know if there's any others. And it looks like there's not. Oh, there is another one. There it is. And so it looks like x equals 1 and what's that other one? Is that 5? Let's check it out. Second trace, and I'm going to do the 0 method. Gonna have to move my cursor closer over here. I'm just not sure if it's exactly 5 is what I'm worried about. Oops, come back. There we are. To the left of it, to the right of it, and hit enter then, and see we're not exactly at. So 5.197. Okay, so now let's put those numbers on our number line. Remember, it's of a second derivative number line. Okay, so I'm going to put these numbers on my second derivative number line, and I'm going to test them. Now remember, the denominators of your second derivative, that was always going to be positive anyway, so we're not really concerned with that. I'm only concerned with this numerator, okay? And so I'll try to put it in here. We'll try to choose easy values, like let's test x equals 0. Right? So I get 0, 0, 0. Positive times a negative is a negative. Then let's do 2. That'll be an easy one there. Positive, let's see, so that gives me 16 minus 32 is negative 16 minus 24 is going to give me negative 40 plus 9, that's negative, and then times a negative is going to give me a positive there. And then let's test x equals 6. Positive. So it looks like I'm going to get a negative here as well. Okay, so remember, this is second derivative we've been testing. That means the function is concave up on the interval from 1 to 5.197. The function is also concave down on the interval from negative infinity to 1, and again from 5.197 to positive infinity. That means I have 2 points of inflection, and those happen at x equals 1 and x equals 5.197. So remember, this looks very, very much like the first derivative test we did with the number line. Only difference is we're doing it with second derivative this time. Okay, let me switch back. We get a little bit more space this way without my calculator. Now, another way to tell maxes and mins is by the second derivative test. So if the second derivative at a number is positive, there is a minimum at x equals a on g of x. Now, here's what I want you to think. Remember, if the second derivative is positive, we are concave up. That means we would have to have a minimum there. Now, the vice versa is true. If the second derivative is negative, then there is a maximum at x equals a on the function. So this is another way to test if you can have a max or a min is based on the value of the second derivative. And here, remember, if the second derivative is negative, it's concave down, there has to be a maximum there. Let's do a couple of these for good measure. So let's see if we can find the first derivative of this would be 4x cubed minus 12x squared. Find your critical points. So we'll factor out a 4x squared. We get x equals 0 and x equals 3. Okay? We did this one earlier, right? We're going to test it with the second derivative now. Take your second derivative, which would be 12x squared minus 24x. And now plug in these values into your second derivative. So the second derivative of 0 is 0. We didn't have anything going on there, right? So there was no max or min. The second derivative at 3 is going to be, let's see, 9 times 12 would give me 108 minus 72. That's going to be positive. That means there is a minimum on f of x at x equals 3. Okay, let's finish up with one more. This one is a trig function. Okay, so we're only going to care about the values between 0 and 2 pi. Again, start with your first derivative, a -2 sine of theta minus 1. Find your critical points by setting the derivative equal to 0. Okay, now we got a good practice of solving some trig functions. So I'm going to bring the 1 over, and I'm going to divide by -2. Then I ask myself, where on the quadrants is sign negative? Sign's negative in 3 and 4. So I'm going to draw my triangle in 3, label my sign to be -1/2. And I know that in my special triangles that across from the 1 is the 30 degree. So that means that this has to be 180 plus 30, which would be 210. I know I have to answer in radians. I'm getting there, okay? I also know that it's negative in quadrant 4. And again, I label my sign, and I get 30 degrees again. But this time, I have to go all the way around. So I have to go here all the way to here. So that's where I do 360 minus 30, and I get 330. Or their radian measures, which would be 7 pi over 6 and 11 pi over 6. Okay, now let's test them with the second derivative. Second derivative would be negative cosine, -2 cosine of theta. Let's plug in these values into the second derivative. Love some good trig functions. Always good practice on those. Okay, so we're in quadrant 3, 7 pi over 6. I'm a drawer. I have to visualize it, right? Would be a 30-degree reference angle. So across from the 30s, -1, 2, and negative square root of 3. So the cosine there is negative square root of 3 over 2, which gives me a positive value. And so that tells me there is a minimum at x equals 7 pi over 6 on f of x. Let's go test the 11 pi over 6 as we finish up. We're plugging it into second derivative. Very important there that we plug it in the right one. We're in quadrant 4. Again, I got a 30-degree reference angle. Label the sides of your triangle. And this time the cosine would be positive square root of 3 over 2, which when I multiply by that -2, I'm going to get a negative value. That tells me there is a maximum at x equals 11 pi over 6 on the graph of the function. So that wraps up our work with a curve sketching. I hope this has helped. If you have comments, as always, feel free to leave them below. I'll be glad to help in any way, shape that I can. Thanks, everyone. Bye bye.